more useful to describe particles describing spherical motion in terms of what are called spherical polar coordinates. Of course, the Schrodinger equation is written conventionally using Cartesian coordinates x, y, z, so that psi is a function of x, y, z. But when you are considering spherical motion, there are three variables now, which we already saw when considering the rotation of a particle on a sphere. That I am repeating now. Suppose the motion of a particle is on a sphere, then the variables are one, the distance from the surface of the sphere, the other, the azimuthal angle, and the co-latitudinal angle called theta. So there are three variables, r, theta and phi. If the motion is on a perfect sphere, obviously r will be constant, whatever it is. For a particle or a point which has the coordinates x, y, z in the Cartesian system, the corresponding coordinates in the spherical polar coordinate system will be r, theta and phi. So it is very important for us to know what is the exact conversion of x, y, z to r, theta and phi. To do that, we have taken, and I am going to erase this to avoid too many pictures on the board. We have taken a point and we are dropping perpendicular to the xy plane AK. Then we are dropping one perpendicular to the z-axis and drawing the appropriate perpendiculars to the appropriate axis. Take 1 or 2 minutes to understand the meaning of this picture. OA is nothing but r. This angle cut by OA with the z-axis is called theta, and the angle cut by OK with the x-axis is called phi. Let us focus on one triangle, which is OMA. So when you consider the triangle OM and A, you will immediately notice that it's a function of theta. So by definition, cos theta is OM by R. So that OM will become R cos theta, but OM is nothing but the z coordinate, and therefore we will get the first relationship, z is equal to r into cos theta. Then we will see that AM and OK in three-dimensional picture are actually same. So OK is equal to AM, but by definition, again considering the same triangle OMA, what is OK? Sorry, what is AM? AM is equal to sin theta by r. So therefore, OK becomes equal to AM, which is equal to r sin theta. This relationship will help us in deriving y and x. Now consider y. Now what is y? Y is nothing but ON, the perpendicular that we drop to the y-axis, ON. That ON is nothing but KL, the two are parallel, although on the board one looks long and one looks short, but in a three-dimensional picture, both are same. And by definition, you can see that KL can be written as OK sin phi, because sin phi is equal to KL by OK. In this triangle of OKL, sin phi is equal to KL by OK, and therefore KL becomes OK sin phi. Substituting for OK, you get y is equal to r sin theta sin phi. By doing a similar exercise, the x coordinate is OL, which is nothing but OK cos phi. And what is OK? OK is nothing but r sin theta. So when you substitute, you will get x as r sin theta cos phi. This brings us to the three very important relationships between the xyz Cartesian coordinates on one hand and the spherical polar coordinates on the other, where we say x equal to r sin theta cos phi, y equal to r sin theta sin phi, and z is equal to r cos theta. This becomes useful particularly when considering the structure of an atom, in particular the description of a hydrogen atom. In the hydrogen atom, when we are forced to write the Schrodinger equation in Cartesian coordinates is converted to spherical polar coordinates by putting these values for x, y and z and doing the appropriate mathematical double differentiations. Then our Schrodinger equation will become an equation in terms of the three variables r, theta and phi. Remember, and I want to reiterate this when we come to the hydrogen atom, the three variables will be r, which can range from 0 to infinity, theta, the colatitude can vary from 0 to 180 degrees or 0 to pi, and the azimuth can essentially sweep an angle from 0 to 2 pi. So within these parameters, within these boundary conditions, we are going to write the Schrodinger equation and solve it, and then find out the wave functions in terms of the variables r, theta and phi. As you can anticipate, the wave function is now depending on two parts. One, it is depending on r. Now what is r? R is the distance from the central point or nucleus in an atom to the surface. The second is the angle. Both theta and phi represent two different angles. So therefore, psi will now be depending on two aspects. One is the radial or the distance aspect, and the other the angular aspect. And out of the two angles, we have already seen for a spherical motion of rotation that theta decides the angular momentum, whereas phi decides the z component of angular momentum, or more particularly the quantum number L decides the angular momentum, and the quantum number ml decides the orientation of the angular momenta with respect to a fixed axis, which we have taken as the z axis. Thank you.